let's look at page 217. They give us a little chart. So using our book, this guy here, we're looking at page 217 and looking at how to find the order of a reaction from a given chart of information. So they give you the balanced equation, 2NO plus Cl2 is 2NOCl. And so we've got 3 trials, trial 1, 2, and 3, and then they give us the information within each trial. I don't know why I put trial up there. 0.1, 0.1, 0.2, 0.1, 0.2. And then they give us the rate for each reaction. And so if you remember when we did the crystal violet lab, all the times we talked about it here, one of the big things that's important is you have to keep one constant while you're worrying about the other, because otherwise you're changing 2 variables and who knows what's happening to the rate because of it. So when you're looking, if we want to know what's happening with NO, Cl2 has to stay constant. So that means we would want to be looking at what's going on in trials 2 and 3. That's great because NO's changing, Cl2's not. So I know anything that happens to my rate is going to be impacted by only NO. Yep. Okay. And so if I were to compare these two, there's 2 ways to do this. There's the quick way where you look to see how this change impacts that change. So for example, what do we see happening here? And then what do we see here? And so if this doubles and this quadruples, then it has twice the impact. And so that would make it a second order reaction. If you're not able to look at that right away, or the math isn't as simple or something like that, then you also could use your rate equations and actually mathematically solve for it. Do you guys want me to remind you how to do that as well? Is that fair? Okay, so if you remember, your rate equation is always going to be rate is equal to K times your concentrations of your compounds. And we're trying to find what their exponents are because that represents the rate of your reaction.
Coach McElroy, please dial 2012.
Okay, so here we know if we kept Cl constant, then I quadrupled, so the likelihood is it's going to be a second order reaction. We could be done and move on, but if not, you could also compare 2 different trials. So we could say, for example, the rate of trial 3 versus the rate of trial 2. I just like to put the bigger one on top because that's just what I like to do. So I'm going to plug in my values. The rate of trial 3 is 1.45, 0.36, and then I know my K's are going to be constant, and my Cl2 is constant. So I'm going to cancel those out. So I just need to plug in my NO value. So I've got 0.2 to the X over 0.1 to the X. And so then when I simplify that down, I've got 1.45 over 0.36 equals 0.2x over 0.1x. So if I simplify that, I've got 4 equals 2x. So the thing that makes x true is if x is equal to 2. So far, so good? Okay. Well, that only tells me what I think NO is. I still have to figure out Cl2. So one of 2 things are going to happen at this point. I'm going to go to my equation, or my chart, I mean, and look for places where NO has been held constant. Fantastically, it looks like trial 1 and 2, it was held constant. So I can see that here my rate doubled. And then here, what happened to my rate? Also doubled. So if they have the same impact on each other, then I know my order has to be what? First order. But if they weren't that nice, and this were an FRQ, they may not have held 2 things constant, in which you'd have to solve mathematically. Because once you know the rate of 2, then you could plug in your values for NO, plug in what its exponent is, since we know it's a 2, and then you would just be solving for the Cl value, which sometimes they're going to do that to you. Does that make sense? Is that enough of a reminder, or do you guys want more? So this would be my rate law. When they ask for the rate equation, they'd have you do this. And then if they wanted you to do like something with it, the likelihood is they'd have you solve for your K value. And so you could plug in any trial, because once you've got it set up, it should be constant as long as these are the parameters.
We have like 4 equals 2 for x. Is there like ever a possibility that x will not be?
There is a possibility, like that does happen, but it doesn't happen very often. So if you got something that's not a whole number, I would double check your work and make sure you didn't do the math wrong somewhere along the way. Once again, doing something that's not a whole number is going to make the math a lot harder, and I have seen AP try to make the math easier. And so they want you to be able to do most of the stuff, even FRQ stuff, without a calculator if possible. That's just what I'm guessing. So, other questions? Is that adequate enough reminder on how to do that, or you guys want any more help with that? Okay, awesome. Then let's talk about the terms thermodynamically favorable. I'm guessing you're talking, when you ask that question, so thermodynamically favorable for internet people, we were remembering that that means it's spontaneous versus non-spontaneous. It's the term that AP's been using. And I'm guessing you guys are asking about delta G, delta H, and delta S. Is that what we're looking at for that? So I did make you guys a chart. I really thought it would be in here. I don't see it in here, where we kind of looked at those. Is that something you would like to have again? Okay. So delta G is basically the guide on whether something's spontaneous or not. Or something's thermodynamically favorable or not. And then delta H, remember, represents enthalpy, aka the heat in your reaction. Not neat, the heat. And then delta S is your entropy. And remember, it's a measure of disorder. Let's see if I can print that for you guys really quick. When we, did we cover this during electricum?
I made like a table of positive and negative.
And I think we did it in electricum. That's the one I was asking you about if you wanted to. What did you say?
We didn't do all the videos because I watched them.
No, we haven't done it yet. No, I meant in real life. Okay, so I put in this little equation, which is a handy thing to have happen. It is one you have access to on your test, I believe. Okay, just making sure. And so it shows your relationship between delta H and delta S. And so if you remember enthalpy, just in general, to be thermodynamically favorable, would we be gaining heat or losing heat? Okay, so when we lose heat, delta H is negative, right? So that's just always, well, always is the wrong word, but usually thermodynamically favorable already when delta H is negative. For delta S, when we want it to be favorable, is it gaining disorder or losing disorder? Gaining disorder. Sorry, I had to remember how I said it out loud. No, you're right. Gaining disorder. Okay, and so when we're looking at that, is delta S positive or negative? Okay, so then if we're looking at disorder, so it's becoming, remember, the more disordered it is, I don't know, entropy is just hard because you're talking about disorder, and so it's tricky. And so that's where this chart kind of comes into play. Notice when our delta H value is negative and my delta S value is positive, then delta G is definitely going to be thermodynamically favorable. And so it ends up being negative as well. If they're the opposite, then the opposite's going to be true. Delta H is positive, that's definitely thermodynamically unfavorable, and delta S is negative, that's not favorable either. So delta G is definitely going to be not thermodynamically favorable. It's just so much easier to stay spontaneous. But when those become the same is where it gets tricky. And so if they're both negative, that means it's leaning towards favoring the delta H already. So in order to make it positive, you're looking for the absolute value of T delta S here that's actually a lower value. So lower temperatures are where that's going to be effective. And when we've got positive values, and for both of them, then we are going to make that spontaneous if your reaction is happening at very high temperatures, because you're providing the energy to overcome the delta H, the energy that was needed to run your reaction. So if you have high temperatures to begin with, then you're going to have that energy that it needs to run, and that's going to make it more thermodynamically favorable. So high temp is going to be, it's going to be negative. Low temp equals negative. This guy, if you think about the fact that at lower temperatures, that is providing your molecules more ability to order themselves because your molecules are naturally moving a little bit slower. So that's also helping to overcome the entropy of your system due to the movement of your molecules. Does that make sense? Let's see if I can show this to the internet world. We were looking at this chart. Enjoy. Do you guys have questions on that? Okay. Remind me, I'll print this for you before you leave so you can have it. Does that take care of the thermodynamically favorable, or were there more questions that came up? That's good. Anybody else? Okay. Then let's move on to collision theory. That's huge. That we put here in this mostly just because it's a unit to talk about it, but it can relate to all of our units. And the idea that in order for reactions to actually occur, two things have to happen. Oh, I forgot to put a sign on the door. Hi.
Hello.
We are doing an AP review session. You're welcome to hang out,
Okay.
but I won't be helpful to you.
Okay. Well, Grace and I were, Grace wanted to come in today to get help on the assignment I was assigned. But
Your hypothesis?
yeah, like, are we just supposed to come up with our exact measurements yet?
No.
This stuff? Okay. I'll text her.
But it's a good place to start if you have an idea.
Okay.
Okay?
All right. Thank you.
Okay. Sorry, everybody. Thank you. Okay, so two things that happen to make your molecules collide. You've got the energy and your orientation. So keep in mind, when you say those things, you should understand in your brain that those are the two things that are going to be applied. But you're probably going to have to explain them beyond knowing the words energy and orientation, because try to remember that these are things that you did learn in general chem, whether you remember it or not. So they're kind of basics, and you want to be able to explain it further than a general chem student could explain it. So why would a reaction need energy to go? Okay, fantastic. Activation energy. And if you remember, our activation energy is basically the energy needed for your reaction to run. And why does it use that energy? Or where does that energy go? Okay, excellent. Because remember, you have to break all of your bonds before they're able to reform with new bonds. Even if some of them are going to connect back together, you have to be able to break all your bonds. And when we break bonds, it takes energy. That's a hugely important concept. Remember that breaking bonds is going to always use energy. So the more bonds we're breaking, the more energy we're going to need. That's only half the battle, because it's not enough just to have the energy. You also have to have the orientation. So when molecules collide, they actually collide in the correct angle and placement so that they're able to interact. And when those bonds break, they can be reformed appropriately. So here, I'm going to say molecules Orientation is the best word to use for that. Correct orientation. And that one is one that is, there are a lot of things to take into play. The molecule shape, what shape they hit and how they hit, and the angles that they hit is all going to be really important. I do not think that's something that you would need to know for the test here. It's probably something you would think about in your later chem classes, maybe when you get into a physical chem type of class or a kinetics energy specific class, depending on what you're doing in your life. So I would anticipate the bulk of your questions are going to be focused on energy and why that's important, and a little bit to understand that the way they hit is still a factor. Once again, that's just a guess. Questions on that? Okay, then I'm going to go to page 218. Okay, this chart at the bottom of 218 is a great chart for a couple reasons. You get a lot of those equations on the test. They used to get all of the equations on the test. So I think it's nice to know that they exist. I gave you a chart that was just like this. I was trying to find it earlier, but I can't right now. But it's fortunately in this book, so you're good. The top is the rate law. That's what we talked about earlier in the game when we were looking at the trials. That's pretty straightforward. You may not get that one particularly, but the integrated rate law, and it tells you the plot you need and the slopes that come from it. So those are all going to be really important that you need to be comfortable with. The plot and the slope, you for sure will be asked some sort of question about it. So I know you guys said you remembered it, so I don't want to spend a ton of time on it. They give you all the reactions for the first order ones. Is that right? I'm just making sure I'm not lying to you. They give you first and second order integrated rate law, and they only give you the half-life for the first order. And they said they were only going to ask you guys about half-lives for first order. But there's your other two equations. I know a couple of you guys were asking me about that half-life question on the test. So here are the equations, so you're comfortable with them, and you can see that concentration is impacted. But I still don't think you have to know the equation, other just than be comfortable with what's in that chart. Questions on that? Okay, super duper. Then let's talk about mechanisms and we'll call it a day. 220 has a couple mechanisms. The basics behind a mechanism, you want to remember this is kind of Hess's law in action. So the goal here is to look at a series of equations that add up to be your overall equation. And so your sum of your equations inside have to match. The slow step always determines your rate. And the only thing that gets kind of tricky about it is when you have an equilibrium type reaction, as in mechanism 2 overall. Oops. So I believe that is supposed to be an equilibrium sign, not a bunch of boxes. And for whatever it's worth, one thing I've seen that could help just in general people is recognizing the difference between this and recognizing that a straightforward reaction can't go backwards. A straightforward reaction is when we're going to use stoichiometry, whereas an equilibrium equation can go backwards, and that's when we're going to use an ice table. So those are the two different types of equations we're going to see, and I just see a lot of people getting them mixed up. So that double-sided arrow is really valuable information because it can help you kind of compartmentalize. Okay, I have to deal with equilibrium, can't here. That's not totally related to mechanisms. That's just me bird walking for a minute. So, okay, so this one is an equilibrium reaction, so we need to look at it. It's a fast equilibrium reaction, so a lot of people want to skip over it and think that it's not important. And this guy here is my slow step. and this is a fast step. So when you see something that's equilibrium, remember that means that has the ability to go back and forth. So what you can do is you could substitute whatever the other side of your equation is into the lower steps within your mechanism. So this is E is essentially saying it's the same thing as A plus B. So I could pull that down here and rewrite this equation as A plus B plus A. So I'm going to rewrite it again as 2A. And now my slow step here, I want to look to see, do my reactants match what I have up here? I should probably make sure you remember what that is. You're nodding, you're shaking your head, so that's good. But remember your coefficients are going to match what my overall rate law is. I didn't write that on here. My jokes. Rate is equal to K squared. Okay, so a couple things. Reminder, you can't use these coefficients to get your order. You have to use these coefficients to get your order. Okay, these are elementary steps. That means they're parts of your mechanism. That's the only time you can use your coefficients. Okay, now, does this match my order? It does. So inserting this equilibrium in allows that reaction to actually run the way it needs to, because this reactant is dependent on those reactants. So it's kind of a way of reminding you all of those reactants are involved in your slow steps. So that does match, and then we would need to consider whether or not the sum of my reactions would actually fall together to meet my overall. What's your question?
Would it be considered wrong if you didn't substitute
E plus A?
Like if you were having to come up with a rate?
And you called it E times A? I would guess that will be wrong, because E isn't one of my reactants, so you couldn't write a rate law with E in it, because the rate law is always going to be based on your reactants. Right, but it's not a reactant in my overall. And so remember, your rate equation has to be based on your overall reaction. So if you were just asked to come up with this, they would expect you to say E is a product, so that means it's got to be A and B. That's a good question. You guys have any other questions about that?
Could you just explain how you got the overall reaction?
It was in the question.
Do they tell you that usually, like on that first page?
Yeah, because what this is asking you, it's giving you two different rate mechanisms, two different mechanisms, I and an II, and asking you to pick which one is the right mechanism. And the first mechanism in your book there, the slow step, is there. None of them are equilibrium. The slow step is only A plus B. So that can't be the right mechanism because it doesn't match my rate law. So then that would help us to lead to the second one is probably the right one, which we just recognize why my orders do match. So if we summed these up, you should be able to cancel it and leave only what's left. So I've got 2 A's here plus 2 B's plus E plus E. So if I summed those, it looks like I've got an E on both sides and an E subscript 2 on both sides. And so then what's left is just my overall, which is just so exciting. So both of those things have to be true in order for your mechanism to be true. We tend to get focused just on the slow step because that's one they often ask us about, but don't forget that you do also have to sum it up.
Can you talk about a catalyst?
Yeah, definitely. So a catalyst would be anything that you start a reaction with that then also comes out the other end of a reaction. So, and I don't know if this one necessarily has. I mean, you could see, since this is your slow step and it happens first, the catalyst is made here. If we wanted to rearrange it, we could kind of look at how this is a reactant here and a product there. It's not really a catalyst, but It's the same idea that you put a reactant in on one end and then it came out later in the game on the other end. So it wasn't used up, it was kind of created during the reaction. It just helps your reaction run faster. So there's often mistaken catalyst and intermediates. Intermediate would be something that's made in a reaction and then used up later in your mechanism. And so you wouldn't ever see it in your overall reaction either, but you just kind of gets there in a different way. Does that help? So factors, I forgot to say, speaking of catalyst, 5 factors that allow a reaction to happen that kind of goes with that collision theory. Catalyst is one of them. Increasing the temperature, increasing the concentration, changing the size of your container, and your pressure are all things that allow, not pressure, size, that kind of goes with the size of your container, the size of your particles. So catalyst, size of container, particle size. Remember, decreasing surface area is better, aka decreased surface area. That's not what I want to say. Increased surface area, decreased particle size. Concentration and temperature. There's that silly video about getting a date to the dance. I know it's silly, but it just sticks with you really well. So I'll put that up when I put up this video. So this, in fact, impacts the rate of your reaction. So it could impact your rate law, but that's why rate can change. That's why we say it only is based on each trial. You have to actually experimentally determine it because there's a lot of factors that affect your rate. Other questions? I think that's everything you guys asked me about. Yes, ma'am. Yes. So, okay. So real fast, the quick thing is a catalyst allows your reactants to react more quickly. So most of the time what a catalyst does is it provides that orientation. So somewhere in the process, it allows your molecules to arrange themselves. Think about an enzyme as a great example of a catalyst. They actually physically have locations that the molecules have to attach to, and then they're able to break in the right order. So that's the most common way a catalyst impacts it. And then we know like temperature is going to impact based on the energy, but most of the rest of these are just allowing your molecules to collide either more often or in the right orientation. So more collisions just naturally equals a faster rate. Anything else? All right. Well, thank you guys. I appreciate you being here.